Section 2 talks about Newton's law of universal gravitation. Newton's law of universal gravitation says that the attractive force between two objects is directly proportional to the product of the masses and inversely proportional to the square of the distance between the object's centers. So the equation is F equal big G, which we'll talk about in a minute, times mass 1 times mass 2 divided by the distance between the object's centers squared. We will sometimes talk about D as our radius. It's going to depend on the problem, but it's going to be the distance between object 1 and object 2's centers, and these objects are going to be revolving or rotating around each other. So this is going to be the distance between the centers of the objects. And I am going to always encourage you guys to stack your variables when you're doing these problems. So I would encourage you not to do this division with a slash like that. I think it typically causes people to make mistakes. This G is going to be a constant number. It's called the gravitational constant. It is 6.67 times 10 to the negative 11, and it has a bunch of units behind it, which we're not going to expect you to know. Mass needs to be in kilograms for both of the objects, and the distance between the centers of the two objects will be in meters. And force, of course, is gravitational force, and the unit will be newtons. So the force exerted by the moon on the Earth is going to equal the centripetal force. And the force exerted on the Earth by the moon is also the centripetal force. So those forces are going to be equal and opposite. And those forces are going to be what cause the two objects to be in rotation around each other. So, first example, what is the gravitational attractive force between Santa Claus, who has a mass of 90 kilograms, mass 1, and Mrs. Claus, who has a mass of 62 kilograms, when they are standing 2 meters apart? So the distance between their centers is going to be 2 meters. We are solving for the gravitational attractive force, and G is 6.67 times 10 to the negative 11 times 90 times 62 divided by 2 squared. Here's where knowing and understanding how to use scientific notation is going to be very important. The answer I got when I'm done with the math is 9.30 times 10 to the negative 8 newtons. You will want to know how to go into scientific notation and how to come out of scientific notation, because you're going to have many numbers that are going to be either super small or super large. So make sure you review how to do that. And if you don't know how, please ask. Next problem is, what's the gravitational force that exists between two spherical 8 kilogram masses? So mass 1 and mass 2 have the same mass. We are going to use the gravitational constant, which is 6.67 times 10 to the negative 11. That's G. Let me rewrite the equation up here. So you're going to do G, big G, M1, M2 over the distance between the two objects squared in meters. So 6.67 times 10 to the negative 11 times 8 times 8. You can also just do 8 squared divided by the distance between the two objects in meters squared. Stop a moment, do the math, make sure that you get the right answer. You will also want to use 3 sig figs in your final answers, the final answer here is going to be 1.71 times 10 to the negative 10th, and the unit is going to be newtons. So Newton came up with the formula that relates the mass of two objects that are in rotation around each other to the distance between their centers. He knew there was a value for g. He lacked the equipment to be able to test for it and to be able to calculate it. But Henry Cavendish was able to design this device where he was able to actually come up with the value for the universal gravitational constant. And you see the units are listed here, Newton meter squared divided by kilogram squared. And it's this super, super small number, 6.67 times 10 to the negative 11 Newton meter squared divided by kilogram squared. So in this device that Cavendish designed in the Cavendish experiment, he used an apparatus where he measured the mass of the spheres M1 and M2, the distance between the spheres R, and the force of attraction F of G. He solved Newton's equation for big G and substituted his experimental values. So this gives you an idea of how he did it. So the gravitational force, we know that gravity is going to be universal and exists between all masses. And so why don't we feel that force in our everyday life? When we're walking by a large building, we don't feel pulled towards it. Why is that? And the reason is that the value for big G is so small that unless one of the objects is super large, like the Earth, then the force of gravity is negligible or small enough that we can't notice it. So we don't feel pulled towards the person sitting next to us. But if we throw something up in the air, the Earth is super, super massive. And so then we see that attractive force of gravity between the object when it falls back to the ground and the Earth. So it has to be a very, very large object involved before we're able to see the effect of the gravitational force. So what causes the tides, and hopefully you're aware of this, the moon causes the tide on the Earth, allowing the waters of the Earth to move. The high tide occurs 2 times per day, and the low tide occurs 2 times per day. Why do they occur at certain times? So if the moon is here overhead, then we experience a high tide. And then when the moon is on the opposite side of the Earth, so it rotates around, this side of the Earth will feel the high tide, but we'll also feel the pull of the moon on the opposite, the 180-degree side from the moon. And are they at the same time each day? No, it's going to depend on where the moon is in its rotation around the Earth. And so they do not happen at the same time. But if you're a fisherman, you can look at a tide chart and you can find out when the high and the low tides will be every day. So Newton's law of universal gravitation can be used to explain the tides, since the water directly below the moon is closer than the Earth as a whole. So that water is going to accelerate more rapidly toward the moon than the Earth, in other words, the ground, and the water is going to rise. The Earth is also going to accelerate more rapidly toward the moon than the water on the far side. And so the Earth moves away from the water, leaving a bulge there as well. And as the Earth rotates, each location on Earth passes through the 2 bulges each day. So gravity is a field force, and the Earth or anything with a very, very large mass will create a gravitational field around it. The forces are caused by an interaction between the field and the mass of the object in the field. The gravitational field G points in the direction of the force as shown. So the gravitational force Fg is directed towards the center of the object, in this case Earth. Michael Faraday came up with the concept that a field is required for a magnet to attract an object. So if you have two magnets with a north and a south pole, we know that like is going to repel. And if you sprinkle iron filings around the magnets, then you'll see the effect of the field forces that are being produced by the magnet. That concept of the magnetic field was applied to gravitational fields, and so anything with a mass has a gravitational field that we can talk about and calculate and describe. We can calculate the value for g, or the acceleration due to gravity, and we do know the force of gravity is calculated using the mass of the object times the acceleration due to gravity. On Earth, that acceleration due to gravity is 9.8 newtons per meter, or we know that it has units of meters per second squared. The value for g on Earth can be calculated using this equation. The acceleration due to gravity is calculated using big G, mass of the planet, divided by the radius of the planet squared. In this equation, what I'm leaving out is the mass of the object. So let's call the mass of the object m of o. M of o. So that is removed from both sides of this equation. And so when I calculate mass of the object times g, that's giving me the weight of the object on the particular planet that I'm calculating. Saturn has a mass that is about 100 times that of Earth, yet its g is still only about 10.4 meters per second squared, which is very close to Earth's. How is that possible? If the Earth had twice its mass, how would that affect the gravitational force on the moon? So if I look at this equation, g equal mass of the planet divided by radius of the planet squared, the only variable that I'm going to change is the mass of the planet. So in my equation, I'm going to make every single variable a 1, but just change the mass of the planet to a 2. So then my acceleration due to gravity on the moon would be 2 times bigger, 2 times bigger. If the Earth were twice as far from the moon, how would the gravitational force of the Earth on the moon be affected? So big G is going to stay the same. It's going to be the constant. The mass of the planet, we're not changing. But the radius now, the distance from the center of the Earth to the center of the moon, is going to be 2 times bigger. And so the radius of the planet, radius between the centers of the planets, is going to be twice as far away, and G is going to be 1/4 as big as it would be. And let me go back up here. I did not talk about Saturn. So Saturn, we're going to make the big G1. The mass is going to be 100 times bigger. And Saturn is much further away from Earth. So this value for R is going to be much, much larger. And that's going to be allowing us to get a number that's relatively close to the acceleration due to gravity on Earth. So we can calculate the acceleration due to gravity on any planet that we have the information for. What is the acceleration due to gravity on Mercury? Using this equation where we have canceled out the mass of the object on both sides of the equation, leaving us with this equation, G equal big G, mass of the planet divided by the radius of the planet squared. And you will be dealing with many very, very small and very, very large numbers. So get out your best exponent calculation skills because you're definitely going to need them. So 6.67 times 10 to the negative 11 is big G. The mass of the planet is 3.3 times 10 to the 23. Make sure that you protect every number that has a big exponent in parentheses, front and back, and that way you will not make a math mistake. Here's the setup for the problem. Go ahead and pause and calculate, see if you get the right answer, and if you don't and you're still confused and need help, please ask. After calculating, you should get a G for the acceleration due to gravity on Mercury of 3.70 meters per second squared. So again, if you didn't get this, this is important to understand how to work this. So check your work. F of G is going to equal mass times G. F of G is going to be the weight. Very important that you guys get that for this unit. Remember, we did use W for weight. It's okay to use it, but I would really prefer if you just called it F of G. F of G is the weight. Your mass is 75 kilograms, and your acceleration due to gravity, small g, is going to be 3.70. When you do your calculation, you're going to get 277.5 newtons for the force of gravity, and most of the time we're going to round to 3 sig figs and use 278 newtons as our answer in this type of question.